Okay, well, good morning, everybody. Today I'm going to talk through some Newman projections. You guys will have a quiz over nomenclature at the end of it. So let's get started. I am going to start with just talking about what a Newman projection is. So let's take this molecule here, throw in some hydrogens. And if you were to take this and you were to rotate it 90 degrees, or you can think of it as, I'm going to try to draw an eye, I'm not good at this. You have an eye and you're looking straight down this bond here. As you go and you look straight down, that bond's going to disappear because you're like looking at it. It's going to look something like in the front. This, and then the back part of your molecule. So let me put some stars, and so we can put a red star here. That's going to correspond to this hydrogen. Because as you're looking down it, if it's coming at you, when you shift it 90 degrees, it's going to be on the left. The other one, I'm going to give it a blue star, should be on the right. The back of our molecule, if I can number these, this is number 1, this is 2. Give you guys some points of perspective. Now we have those 2 hydrogens in the back. These 2 here. Let's see. Oops. I'm gonna give one of them a green star. So this one that is on a wedge here, it'll be in the same plane as, or the same side of your molecule as the other one that's on a wedge. So it should be here. And then let's see if I can get yellow to show up. It's not the greatest, but I need to work on my stars. Yeah. Okay. So this is what our Newman projection is. It's a representation of looking directly down this bond line. There are 6 different conformations of a Newman projection, and they are all going to be based on, what is it, 60-degree rotations? I think you're doing 60-degree rotations. So let's start by just taking a look. I'm just going to redraw without all these stars. Like so. So same thing we just drew to cover all the stars. In order to do Newman projections, my advice is take the front of your molecule and redraw it 6 times. Or I guess 5 more times. You could also do this at the back, but really it's more important that you pick one. So from this point, we are only going to move the back half of our molecule. And by the back half, I mean everything that's coming out. So these three components here, we are not going to be touching. I'm going to circle them in blue. The front half of your molecule, obviously, because we just drew it out 5 more times. And we can throw in this circle. Okay. So step 1 for drawing your Newman projections, you are going to rotate 60 degrees and always go the same direction. I'm going to go clockwise. I think that's just easier. If I shift this 60 degrees, this H 60 degrees, this CH3 60 degrees, they're going to go from being what's called an eclipse conformation to being a staggered conformation. So they're going to be more on top of each other. So we moved, the number of the H's. Let's go 2 and 1. We moved H2 over, sorry, H1. I mean, I'm losing it. 60 degrees, and now it should be over here. We moved H2 clockwise and down. And our CH3 gets moved, everything gets moved clockwise to this position here. So we rotated everything 60 degrees. That pushed our back molecule, well, 60 degrees. If we do this again, so we're going to take H1, shift it another 60, H2, shift it another 60, CH3, shift it another 60. I'm going to draw it over here. Now H1 is over here. We've rotated 60 degrees again. We can keep doing this. So pushing this one, pushing this one, pushing this one. That gets us to having the two CH3s next to each other, two H's, like so. So we went down again. Let's see, this is H1, this is H2. Another 60 degrees, puts us into another staggered conformation. We can rotate one more time. Technically twice more. It's going to get us to our final eclipse conformation. If we rotate yet again here, so this should be H1, H2, rotating one last time is going to bring us back to the start. So this is our cycle. We're slowly moving the back part of our molecule 60 degrees until we get back to where we started. Any questions on this so far? Okay. I'm going to erase some of these lines and then talk about some energy levels. Okay, so we can break this in half. Everything on the top is staggered. And by staggered, I mean that there's this space here between all of your molecules. They're all spaced 6 degrees apart. Versus on the bottom, everything is on top of each other. Which is what's called eclipsed. And if you think of like a solar eclipse or a lunar eclipse, it's where the sun passes in front of it. So these two CH3s are passing on top of each other. So the top CH3 is going to be blocking the back CH3. And technically, you should only be able to see the front of the molecule. All right, so now when we look at these, we're going to group them by energy. The ones in the, so all the staggered are going to be lower energy. Just because it's easier for those hydrogens or carbons to be spaced apart than it is for them to be on top of each other. So this part down here where all the eclipses are is going to be a higher energy part. If we take a look at the molecules themselves, we're really going to focus on the CH3s. We don't really care about the H's that much. So we're going to look at interactions with CH3s with each other, for the staggered at least. So for the top part here, this CH3 I'm circling, it's next to 2 hydrogens, so that really doesn't get much of an interaction. It's really easy for it to be next to those 2 hydrogens. So there's no like energy cost to being in this position. Versus the next one where we have these 2 CH3s next to each other, that's going to be a higher energy level than it is to just have your CH3s be by themselves and have no neighbors that are causing you any sort of like repulsion. Same thing on the other side. These CH3s are next to each other, which are going to repel each other. So taking a look at our staggered conformations, if I was to rank them in terms of energy, I don't know, we could say 1, 1, and 3. These two are both have in the CH3 interaction versus this one that's on the far left has none. Later we'll do an energy diagram and you'll kind of see how we rank them, but the middle one and the right one have the same energy requirements versus the one on the left, which has the least amount because it doesn't have any interactions. Okay, so we're doing kind of the same thing on the bottom. CH3 interactions are going to cause a lot more strain than HH or a CH3H interaction. So immediately, this interaction here should kind of jump out at us as a high energy interaction versus our 2 other molecules. You have, I'll draw them in blue, circle them in green because it's not as much of an interaction. These are like weak interactions. These are weak interactions. But that one that we circled in red was really our strongest interaction for these. Okay, so I'm going to take this and I'm going to put it into an energy diagram, which I believe you guys did in class. Not in green. Actually, you know what? I can use this. I'll erase these. No, I'm just upside down. I'm going to redo it. Okay. So we're going to start with the conformation. One of our stagger conformations, the one we started with originally. To kind of, I'm going to make a line between our eclipsed and our staggered. So if we're here, we rotate once, we're going to get 2. So redrawing our top, because that's always the same. We're now doing eclipsed. We can rotate again. It's going to take us down below to a new staggered. An easy way to kind of think about this one is we're slowly moving this guy around. He's now here. Oh, I'm staggered. We can have one more position down here he can be in. And then our last possibility on our eclipsed. Would be this. So let's break down our interactions again. So we said that on our staggered, that these 2 interactions are going to be stronger than these 2 CH3s. So when we draw energy diagrams for these, I'm going to draw the energy in green. This one with all the blue circles will give you our lowest energy. The ones with our 2 CH3 interactions, we can put them higher up. If we move back over to our eclipsed conformations, I can delete just this. Oh, we said that this CH3 CH3 interaction is a lot more extreme than the other 2. That's going to take a lot more energy, which means that this is going to be a lot higher in energy than these 2. And then for generating, oops, I need one over here. Your energy diagrams for these, you're literally just going to connect the dots. So I'll do it in blue. This would be an appropriate energy diagram for this Newman projection. You guys did talk about energy diagrams, right? Hopefully I didn't just spend 10 minutes talking about that. Anybody awake?
We touched on it a little bit.
Okay. And you may go over it more tomorrow. You may not go over it too much. I can focus more on the actual drawing of the structures. So let's take a minute. I'm going to put one up and have you guys just draw out your first Newman projection for it. So let's put up a new structure. Oh God, it's a terrible 3. Okay, so if you were to get this molecule on an exam, you are asked to look down this bond here, try and draw a Newman projection from this. I'm going to give you guys, I don't know, a minute or two. Draw a staggered one. All right, so if we're looking at the front of our molecule, that CH3 is going up. So it's going to be into this position here. So maybe we'll star. This CH3 is going to equate to this CH3 here. Our CH3 is on a wedge coming at us. If you think of it, we're like turning the entire thing from here to here. Now it's going to be pointing to the left. Which leaves that blue H on the right. Back of our molecule is going to follow a really similar trend. So CH3 would be on the bottom. Our wedges are going to be the same. So if the CH3 that I have a little red star next to is a wedge and it's on the left, that means that H is also going to be on the left. In this case, there's 2 H's, so it's not as much of a big deal. But that should get us to this Newman projection. Any questions so far? Okay, I'm going to redraw this one real quick. Okay, I'm going to give you guys about 5 minutes to go through and try to draw the rest of the Newman projections for this. So go through, rotate it all the way around, and then we will do a little bit of analysis and try to generate an energy diagram from it. All right, so I filled in some of it. So I like to keep the front the same and just rotate the back. Like I said, so I've redrawn the front 5 more times, kind of broken it into staggered and eclipses. If I take this back molecule, rotate, 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 that CH3 is now going to be here. The other two are just H's. Rotating clockwise again. That's your CH3 here. Rotating another time. Moves it up to the top. Now we're going to be bottom, nope, middle, I don't know, like northeast. And last one is going to be bottom right. Okay, so let's take a look at some energies here. Start with first let's go start with the stagger ones first. Taking a look for interactions, carbon-carbon interactions. We have one here. We have one here and one here. And we have just one on this one. So our middle one has 2 interactions. The 2 outside just have 1. Which means this one's gonna be higher energy than these 2. Looking for carbon-carbon interactions on our eclipsed. We got 1 here, 1 here, none on the last one. So these 2 are going to be higher energy than the last one. We can connect the dots. Like so. All right, I'm going to draw up one more of these molecules. Have you guys work through it. And then I will probably kind of work simultaneously like I did in this one. So if you get stuck at any point in time, I'll draw the first one by like the first couple of minutes you guys are going through it, and then we can look at it together as we go. So let's do this molecule. I'm gonna have you look. Oh, that's not the draw. Looking down this position here. Get some eyelashes. I will check in with you guys in about 4 minutes. I'll kind of, in about a minute, start drawing parts of it so you guys can make sure you're on the right track. All right, I got the first one drawn if anyone wants to make sure they're on the right track. All right, so based on our starting structure, now we have two CH3s that are rotating because there's two in the back. Honestly, I'm just gonna focus on the hydrogen because that's gonna be easier. That's by itself, and then everything else is a CH3. So rotate this guy down. He goes to here, and then I have two CH3s. He's then gonna get shifted to the bottom. He'll go, I don't know, southwest. And then northwest. Followed by completely north. Okay, so from here, we're looking at interactions. Starting with our staggereds, we've got 1, 2 for this first one, 1, 2, 3 here, and 1, 2, 3. So that means 2 and 3 are higher energy. Take a look at our eclipsed ones. We've got a CH3, CH3 for this one. We've got 2 of them on this one. And just 1 of them on this one. So our middle one's high energy. The other 2 are lower. Making an energy diagram, going to connect the dots. So start here. And that'll get us through all of our conformations and our energy diagram. Okay, I'm going to have you guys turn on your cameras. We're going to take a quick quiz. I'll leave this up for a second if anyone wants to take like a screenshot or a photo of it. All right. Let's see. We're doing some naming. So naming of these two structures here. Oh, shit.
Oh yeah, Matt, is our quiz like able to turn in yet?
Yeah, 1 second. I just realized I didn't make it yet. Yeah. So,
Okay, it should exist now.